there are two theories on how we make planets. So we got to go from gas to this. It started with what's called the nebula theory, and people have been thinking about this since the 1700s. The most popular ones that we have here is the gravitational instability model and the core accretion. Now, the gravitational instability model, well, let me just skip ahead. Basically, a planet forms like a star. And this was meant to try to explain Jupiter. We have to form Jupiter first in our solar system because Jupiter is like the big brother in the sandbox. Once Jupiter formed, things kind of settled out, and then everybody could start doing their formation thing. So what they did was, these are computer models, and these are screenshots of a protoplanetary disk rotating. And you can see that as it's rotating, put in the physics, put in the chemistry, put everything, push start on the computer or your computer code, and you could see that you get some kind of objects. In fact, let me play it for you. Doesn't take too long. You can make Jupiter in 500,000 years. Told you it's easy. Only problem here is with the gas instability model is the conditions for the instability to start making these planets is not what we had in our solar system from what we get from observations. And we know there are solids in Jupiter and Saturn, Uranus and Neptune, and we have solid planets. So where did the solids come in? How do you, once you have Jupiter, a big old gaseous Jupiter, how do you get the solids in there? So it keeps us kind of honest in the core accretion business. So any model has to explain the mass distribution. You have to make these planets anywhere between 3 and 10 million years, and the protoplanetary disk people want us to make these planets in about 5 million years, anywhere between 3 and 5 million years. Got to make them fast. We got to explain that these are solids here, that you have some gases here, and then these guys are kind of icy. So this is the core accretion model. I didn't want to boast early, but this is our model. This is what we've done. We start off with planetesimals that are about a kilometer size big. And what we're doing is we're accreting it onto a moon-sized core. And it keeps getting bigger and bigger until it's massive enough to hold on to whatever gas it is inside its feeding zone. And as this feeding zone, as the planet gets bigger, its feeding zone gets bigger. And it's able to accrete, and at this point, Jupiter is about 200 times bigger than it is right now. So it's really spread out. But eventually, it runs out of solid material, it runs out of gas. So it can't feed it, so there's nothing there to keep it puffed out. It collapses, and we form Jupiter. Good, we could do it. What about terrestrials? Something the gas instability model can't do. Well, you start out the same way. Again, it's Occam's razor. Keep it simple. Why should there be one model for the gas giant, and why should there be for a terrestrial? So again, you start off with the planetesimals. They're always there. The solid material is always there. And then what you're doing is you're waiting for the gas, but there's no gas because these are terrestrials close to the sun, and all the gas is gone. It's vaporized. And you're left with a rock. We've got Earth. So you've got one theory, one model that can explain the whole solar system. Ta-da. It also explains that we have the asteroid belt. Those are leftover planetesimals that didn't go anywhere. And the asteroids were close to the sun, so there aren't that much gas and ice on them. The comets are further out, and they're cold, so they could keep their ice. So all in all, big question was, once we started finding the other planets, can we explain it? And we still can. The core accretion is the model that is still acceptable as the working model for planet formation. What I wanted to do, but I'm just going to speed this up, is this is what things start out with. These are space grains. These are millionths of a meter big or small. These are microns. And each one of these is dust from space. And we know they're dust from space because their composition is not what we have here on Earth. Totally different. So these guys are floating around in the gas. They get bigger and bigger and bigger. And what they do is they move kind of slowly. Neil deGrasse Tyson in his Cosmos had a really good animation about how he showed all these planetesimals. And you'd think that they go really fast, but you don't want to, because if they're going fast, they're going to crash and they're going to break apart and you got to start all over again. You want them to come slowly, gently together, gravitationally come together and get bigger and bigger and bigger. So we can do this. We see that it's being done, but there's a problem here. The observers of all of these say, we don't see any dust in any of this after about 10 million years. So that means if there are any planets, they've got to be made. And so we did it. What this is an animation from our work. We're almost over here. We're almost finished. This is an animation. I showed an animation of the gas instability strip. I got to show our work too. And what I'm going to show on the next slide is over here is the time. And this is the mass. So you can watch on the graph as the planet grows. And what this is just showing the different kinds of the temperature change. And so let me just get this going. Notice we're able to get it done in 2.5 million years. So plenty of time. And this is a model for Jupiter. So once I get this animation going, so you can see it slowly, and it's beginning, and it's kind of gets big pretty fast, and then it slowly increases, and it's slowly going through, and it's building up gas. At this point, all it's doing is collecting gas. There's only about 12 Earth masses of solids inside. And then it goes, and then it starts really increasing, shuts down, and we got Jupiter. So, and we did it in 2.5 million years. So you say, what's the big deal? It's solved, no problem. Well, there is a problem. What happens is it takes a very long time for these little guys to get to a point where they're planetesimal size. We know they did it because we're here, but we haven't figured out exactly all the mechanism for it. Because some of the models right now build it up to be about 1 kilometer size, and then they'll crush themselves. So we can't get it up to 100-kilometer planetesimals yet, but they're working on it. And so since we see the planet, we know it's there. It wasn't a miracle. We know it's got to be there. So I just want to leave you with this idea that this is our solar system. It's an incredible place. Whether Pluto is a planet or a dwarf planet or just a rock, it's every piece of anything in this solar system is worth that 1/10 of 1 penny of NASA's budget. It is, we live in an extraordinary place. So now you know. Thank you.
So thank you very, very much.
Thank you.
You've made many important points.
Oh, good.
One, certainly that a teacher really helps the learner.
Uh-huh.
So we understand why you were such a distinguished
Oh, thank you.
lecturer in
Thank you. Thank you.
2014.
Thank you.
Yes.
Thanks.
You've also made the important point about science funding.
Oh.
So on behalf of SRI, I had to really point that out.
Thank you for
benefit
supporting
from
that.
science funding. And we'd like to thank you, just a token of
Oh,
our thanks, the
thanks.
Cafe Sci mug.
Thank you.
You probably stay up at night observing the stars.
I'm a theoretician.
You're a
I do everything in the morning.
Okay. Well, that's for your morning coffee.
My morning
Okay.
coffee.